Error handling. Errors are a fact of life in software, so Rust has a number of features. For handling situations in which something goes wrong. Errors are a fact of life. Errors are a fact of life in software, so Rust has a number of features. Errors are a fact of life in software. Errors are a fact of life. Errors are a fact of life in software, so Rust has a number of features for handling situations in which something goes wrong. In many cases, Rust requires you to acknowledge the possibility of an error. And take some action before your code will compile. In many cases, Rust requires you to acknowledge the possibility of an error and take some action before your code will compile. This requirement makes your program more robust by ensuring that you will discover errors and handle them appropriately before you've deployed your code to production. Rust groups error into two major categories, recoverable and unrecoverable errors. For a recoverable error, such as a file not found error, we most likely just want to report the problem on the user to the user and retry the operation. Unrecoverable errors are always symptoms of bugs, like trying to access a location beyond the end of an array, and so we wanna immediately stop the program. Most languages don't distinguish between these two kinds of errors and handle both in the same way, using mechanisms such as exceptions. Rust doesn't have exceptions. Instead, it has the type result. For recoverable errors and the panic macro that stops execution when the program encounters an unrecoverable error. This chapter covers calling panic first and then talks about returning result values. Additionally, we will explore considerations when deciding whether to try to recover from an error or to stop execution. Most languages don't distinguish between these two kinds of errors and handle both in the same way, using mechanisms such as exceptions. Rust doesn't have exceptions. Instead, it has the type result. For recoverable errors and the panic macro that stops execution when the program encounters an unrecoverable error, this chapter covers calling panic first and then talks about returning result values. Additionally, we will explore considerations when deciding whether to try to recover from an error or to stop execution. Wait a second. Instead, it has the type result for recoverable errors and the panic macro that stops execution when the program encounters a recoverable error. This chapter covers calling panic first and then talks about returning result values. Additionally, we will explore considerations when deciding whether to try to recover from an error or stop execution. Okay. Unrecoverable errors with panic. Sometimes bad things happen in your code, and there's nothing you can do about it. In these cases, Rust has the panic macro. There are two ways to cause a panic in practice: by taking an action that causes our code to panic. By taking an action that causes our code to panic, such as accessing an array past the end. Or by explicitly calling the panic macro. Or by explicitly calling the panic macro. In both cases, we cause a panic in our program by default. These panics will print a failure, or by explicitly calling the panic macro. By taking an action that causes our code to panic, such as accessing an array past the end, or by explicitly calling the panic macro. In both cases, explicitly calling the panic macro, there are two ways to cause panic in practice: by taking an action that causes our code to panic. This is accessing rise. Okay. In both cases, we cause a panic in our program. Um, by default, these panics will print a failure message on wind, clean up the stack, and quit. Via an environment variable, you can also have a Rust display the call stack when a panic occurs to make it easier to track down the source of the panic. You can also have Rust display. You can also have the Rust display the call stack when a panic occurs to make it easier to track down the source of the panic. Unwinding the stack or aborting in response to a panic. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up the stack and clean up the data from each function it encounters. However, this walking back and cleanup is a lot of work. Rust therefore allows you to choose the alternative of immediately aborting, which ends the program without cleaning up. Memory that the program was using will then need to be cleaned up by the operating system. If in your project you need to make the resulting binary as small as possible. You can switch from unwinding to abortion upon a panic by adding panic equals abort to the appropriate profile sections in your cargo.toml file. For example, if you want to abort on panic in release mode, add this. Let's try calling panic in a simple program. When you run the program, you will see something like compiling panic. Finish the running target target debug a panic, share the main panic that crash and burn. Run with Rust backtrace environment variable to display a backtrace. The call to panic causes the error message contained in the last two lines. The first line shows our panic message and the place in our source code where the panic occurred. src main.rs2.5 indicates that it's the second line fifth character of our src/main.rs file. In this case, the line indicated is a part of our code, and if we go to that line, we see the panic macro call. In other cases, the panic call might be in code that our code calls, and the file name and line number reported by the error message will be someone else's code where the panic macro is called, not the line of our code that eventually led to panic call. We can use the backtrace of the functions the panic call came from to figure out the part of our code that is causing the problem. We will discuss backtraces in more detail next. In this case, the line indicated is a part of our code, and if we go to the line, we see the panic macro call. In other cases, the panic call might be in code that our code calls. When you run the program, you will see something like this. The call to panic causes the error message. When you run the program, you will see something like this. The call to panic causes the error message contained in the last two lines. The call to panic causes the error message contained in the last two lines. The first line shows our panic message. Message and the place in our source code where the panic occurred indicates that it's the second line. 50 character. Fifth character. Fifth character. Okay, makes sense. In this case, the line indicated is a part of our code, and if we go to the line, we see the panic macro call. In other cases, the panic call might be in the code. In the other cases, the panic call might be included or code calls, and the file name and line number reported by the error message will be in other cases, the panic call might be encoded or code calls. Call might be encoded or code calls. And the file name and line number reported by the error message will be someone else's code where the panic macro is called, not the line of our code that eventually led to the panic call. We can use the backtrace of the functions the panic call came from to figure out the part of our code that is causing the problem. We will discuss backtraces in more detail next. Using a panic backtrace, let's look at another example to see what it's like when a panic call comes from a library because of a bug in our code instead of a form. From our code calling the macro directly, listing 9-1 has some code that attempts to access an index in a vector beyond the range of valid indexes. Using a panic backtrace, let's look at another example to see what it's like when a panic call comes from a library because of bug in our code instead of from our code calling the macro directly. Listing 9-1 has some code that attempts to access an index in a vector beyond the range of valid indexes. Here we are attempting to access the 100th element of our vector, which is at index 99 because indexing starts at 0. But the vector was only 3 elements. In this situation, Rust will panic. Using bracket is supposed to return an element, but if you pass an invalid index, there's no element that Rust could return. Here, that would be correct. In C, attempting to read beyond the end of a data structure is undefined behavior. You might get whatever is at the location in memory that would correspond to the element in the data structure, even though the memory doesn't belong to the structure. This is called the buffer overread and can lead to security vulnerabilities if an attacker is able to manipulate the index in such a way as to read the data they shouldn't be allowed to, that is stored after the data structure. To protect your program from this sort of vulnerability, if you try to read an element in an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. To protect your program from this sort of vulnerability, if you try to read an element, to protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. Rust will stop execution and refuse to continue. Let's try it and see. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. Thread main panicked at index out of bounds. The len is 3, but the index is 99. This error points at line 4 of our main.rs where we attempt to access index 99. The next note line tells us that we can set the Rust backtrace environment variable to get a backtrace of exactly what happened to the caused error. A backtrace is a list of all the functions that have been called to get to this point. backtraces in Rust work as they do in other languages. The key to reading the backtrace is to start from the top and read until you see files you wrote. That's the spot where the problem originated. The lines above that spot are code that your code has called. The lines below are code that called your code. These before and after lines might include the core roster code, standard library code, or crates that you are using. Let's try getting a backtrace by setting the Rust backtrace environment variable to any value except 0. Listing 9-2 shows our output similar to what you will see. Wait a second, okay. Instead attempting to read beyond the end of the data structure is undefined, okay. So element data structure even though the memory doesn't belong to the structure. Okay. This is called buffer overread and can lead to security vulnerabilities if an attacker is able to manipulate the index in such a way as to read data they shouldn't be allowed to. So that is stored after the data structure. To read the data, they shouldn't be allowed to that. It's stored after the data structure. If an attacker is able to manipulate the index, if an attacker is able to manipulate the index in such a way as to read data, they shouldn't be allowed to read that. This is called a buffer overread and can lead to security vulnerabilities if an attacker is able to manipulate the index in such a way as to read data they shouldn't be allowed to. That is stored after the data structure. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist. To protect your program from this sort of vulnerability. To protect your program from this sort of vulnerability. To protect your program from this sort of vulnerability, if you try to read an element at an index, this is read to security vulnerabilities. If an attacker is able to manipulate the index in such a way to read the data, they shouldn't be allowed to. That is stored after the data structure. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Russia will stop execution and refuse to continue. Let's try it and see. To protect your program from this sort of vulnerability, if you try to read an element at an index, to protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution. If you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try it and see. Okay, sure. Uh, Index out of bound. Okay. So this error points to line 4 of our main.rs where we attempt to access the index 99. The next node line tells us that we can set a roster backtrace environment variable to get a backtrace of exactly what happened to cause to the error. A backtrace is a list of all the functions that have been called to get to this point. Backtraces in Rust work as they do. Do in other languages. Backtraces in Rust work as they do in other languages. The key to reading the backtrace is to start from the top and read until you see files you wrote. That's the spot where the problem originated. The lines above that spot are code that your code has called. The lines below are code that call your code. These before and after lines might include the core Rust code, instead of library code, or grade that you are using. Let's try getting a backtrace by setting the Rust backtrace environment variable to any value except 0. Listing 9-2 shows an output similar to what you will see. Cargo run. The backtrace generated by a call to panic displayed when the environment variable Rust backtrace is set. That's a lot of output. The exact output you see might be different depending on your operating system and Rust version. That's a lot of output. The exact output you see might be different depending on your operating system and Rust version. That is a lot of output. The exact output you see might be different depending on your operating system and Rust version. In order to get backtraces with this information, debug symbols must be enabled. Debug symbols are enabled by default when using cargo build or cargo run without released flag as we have here. Main panic that index of that's a lot of output. The exact output you see might be different depending on your operating system and your version. In order to get backtraces with this information, debug symbols must be enabled. Debug symbols. Debug symbols are enabled by default when using cargo build or cargo run without release flag, as we have here. In the output in listing 9-2, line 696 of the backtrace points to the line in our project that's causing the problem. In the output in listing 9-2, in the output in listing 9-2, line 6 of the backtrace points to the line in our project that's causing the problem in line 4 of the assortment arrays. If we don't want our program to panic, we should start our investigation at the location pointed to by the first mentioning a file we wrote in listing 9-1, where we deliberately wrote code that would panic. The way to fix the panic is to not request an element beyond the range of the vector indexes. When your code panics in the future, you will need to figure out what action the code is taking with the what values to cause the panic and what the code shouldn't do instead. We will come back to panic and when we should and should not use panic to handle error conditions in the to panic or not to panic. Okay. Later in this chapter, next we will look at how to recover from an error using result. What is the name of the environment variable? You should get set to 1 to see the batteries of the panic. Rust batteries. Which of the following is not a good reason to use a panic? The program is about to perform a dangerous operation. Which of the following is not? The program should stop executing as soon as possible. The program has reached an error state which should be communicated to caller function. The program has reached an unrecoverable error state. Okay, correct. The program has reached an error state which should be communicated to a caller function. Yes.